In this lesson, we need to review factorising and make sure that we're really good at it before we go any further in this course. So before we start, what are factors and what in fact is factorising and why do we need to do it? Well, factors come in pairs. They're two numbers or two terms that you can multiply together to make some larger term. So by factorising, we're basically turning some expression that might have several terms added or subtracted, we're turning it into a multiplication problem. We're turning it into something multiplied by something else. Now, why would we need to do this? Well, two main reasons. You might need to do this if you're simplifying a fraction. So let's have a look at a complicated fraction up here. Now, to simplify it, we need to factorise the numerator and the denominator separately so that we can see if they have any common factors. Don't ever think that you can just fall for randomly cancelling or crossing out terms that appear on the top or the bottom. It would be a hideous crime to cross out the x squared on the top and the bottom there. We know that you can't do it. And if you're ever thinking about falling for that sort of trick, ask yourself a question that's a lot easier. If I have something like this, let's make a nice simple fraction that's just got numbers in it. I know that this is 3 out of 6, which is equal to a half. If I was to take the 2 and the 6 though and say, oh gee, they're both even, perhaps I can halve them. What I'm left with then is 2 on the top and 3 on the bottom, and 2/3 is certainly not the same as a half. So if I'm going to halve this term and halve this term, I'd have to halve this one as well. And then I'd have 1.5 out of 3, which is equal to a half. So you can't just pick and choose which terms you want to just cross out or cancel. And in fact, that term cancelling, when people use that word and they sort of think about just getting all happy about crossing things out, you need to make sure that what you're saying to yourself as you cross something out is, I'm going to divide the whole numerator by this, and I'm going to divide the whole denominator by the exact same thing. So what we need to do first is to turn this plus and minus expression here into a multiplication problem, something times something. So I can see here it's a monic quadratic. We've learned how to factorize those before, and it factorizes out as x plus 2 multiplied by x plus 3. On the bottom, I've got the difference of two squares, which I can recognize is x plus 3 multiplied by x minus 3. So I can divide the entire top and the entire bottom of the fraction by x plus 3 there. And that just leaves me with x plus 2 over x minus 3. And I've got this rather complicated looking fraction looking a whole lot simpler. Why else would we want to factorize? Well, it might be that we want to use the null factor theorem to solve an equation. Now, similarly, here I've got a non-monic quadratic trinomial, which trinomial just means 3 terms. It's quadratic because it's something squared. And I've got a plus and minus expression here that's equal to 0. And it's not easy to solve that just by thinking, what number can I square, then subtract one lot of that number, and then subtract 2 and get 0. That's not easy to do. But by factorizing, in other words, turning it into a multiplication problem, something times something, now I can use that null factor theorem. Null means nothing. Factor, yep, I've got two things that are multiplied by each other, and the theorem says if something multiplied by something else is equal to 0, one of those parts must have been 0. So either the x plus 1 part must have been 0, or the x minus 2 part must have been 0, in which case here the x would have to be -1 to make this little equation true, or it would have to be 2 to make that equation true. So very easy to solve once I use that null factor theorem. X is equal to -1 or 2. So we've got two good reasons there for factorising, and it might be that you've got an equation that's got fractions in it. You might need to actually use it for both reasons. Now, key steps. Can I just reiterate that these key steps are like a little checklist. Even though you know how to do all these things already, I'm reminding you what to do in what order. Always look for a common factor in all the terms first. Whether or not you've already spotted, hey, it's a quadratic, whether or not you've spotted, hey, it's the difference of two squares, always pull a common factor out the front of your brackets first if you can. Check for the difference of two squares. So if you found that you don't have a common factor, all you really need to find the difference of two squares is you need one term minus another term. So if you have it in this form, a squared minus b squared, then we've learnt that that factorizes out as a plus b multiplied by a minus b. So check for that. Is it a quadratic of this form, ax squared plus bx plus c, where a, b, and c are just numbers? So in other words, is it something squared? Now, if it's a monic one, a will be 1. It might just be x squared something something, or if a isn't 1, it's a non-monic. And we've learnt two slightly different methods for factorising those. We'll review those in a minute. Can you form two pairs of terms that each share a common factor? Now, this might happen if you've got, say, 4 terms, and you can't see how to factorise it any other way. This is a backup. And then once you've been through this list, basically go through it again, because you'll need to check that you have fully factorized an expression when you factorize it. So it might be that you've actually done some factorizing, but you're not all the way there yet. Now, how do you tell when you're fully finished? Well, you can tell you're finished because the expression that you get in brackets, those terms that are inside the brackets shouldn't share any common factors. So up here where I did some factorizing, I can see that x and 2 share no common factors. So you can tell you're finished. And if you're not finished, it may be that you didn't do this and you can pull a common factor out later on. So a bit of a checklist. Let's look at some examples now to check that we can factorize all of the different basic forms. Okay, some examples of each type. So the first one, I need to just pick out a common factor, and I can see that both of these terms have 3 in common, but they also both have at least one x. So I can bring 3x out the front of my brackets, and whether you choose to say, look, let's divide this term by 3x and see what we get, and divide this term by 3x and see what we get, and put what you get inside there, or whether you choose to actually just expand with an unknown. Say to yourself, 3x times something is 3x squared. Oh, I know, it's x. Same process, slightly different thinking. Do it whichever way you're comfortable with, but what I do recommend doing is when you think you're finished, expand it out to check that you get what you started with. So 3x times x is 3x squared, 3x times negative 4y is negative 12xy, just to be sure that you've got it right. Okay, the next one, there's no common factors, but I looked for them just in case, and I can see that this is the difference of 2 squares. So I've come to see over time that that gives me this sort of shape where I need to take the square root of the first term and put it as the first term in both sets of brackets, and the square root of the second term, which in this case is 4, and then I have a plus in one set of brackets and a minus in the other set. And the reason this works out, the first term, x times x is x squared, and the last term, positive 4 times negative 4 is negative 16. The inside and the outside terms, as we call them when you do your FOIL method, firsts, outsides, insides, and lasts, well, the outsides and the insides are going to always cancel each other out because we've got the exact same 2 terms, except one is plus and one is minus. The next one is a monic quadratic trinomial. So it's a quadratic, something squared, it's a trinomial, it's got 3 terms, and it's a monic one because I've got just a 1 out the front here. Now with those, I've learnt just to draw up my set of brackets like this. I can see that the first term in both sets of brackets needs to be an x, and I will jump straight to the last term in each one here and say that I need to have 2 numbers that multiply together to make 12, but I know that they need to add together to make minus 7. So a quick sketch out of what your factors of 12 are. Which 2 can I use here to make minus 7? Well, clearly only 3 and 4 can make minus 7, and they can only do so when they're both negative. So negative 3 and negative 4 looks like my answer. I'm never fully sure until I expand it out again just to check I get back to where I started. So negative 3x and negative 4x is negative 7x, and then negative 3 times negative 4 gives me the positive 12, so I'm good. Okay, the next one, I need to check whether I can divide all of the 3 terms by a common factor and bring it out the front, but I can't. So that means it must be a non-monic quadratic trinomial. Non-monic because there's a 2 out the front here, and that gives me a slightly different method for these. Trinomial, there's 3 terms, and quadratic, there's something being squared. So I've learnt with these that I need to multiply the 2 and the negative 4 together to get negative 8, and I need to find factors of negative 8 that add up to 7. So the factors of 8, 1 and 8, 2 and 4, the only way I can make 7 out of that is with the 8 and the 1, and I need to do it by having positive 8 and negative 1. So I'll start by changing that 7x into 8x minus an x. I just rewrite it like that, and it makes no difference which way around these go. Next, I need to just treat this as a pair and factorize them, treat those as a pair and factorize them. But I need to make sure I've got the same thing in brackets both times. So just treating these as a pair, I can bring 2x out the front of x plus 4. But then I know that I need x plus 4 as my second set of brackets as well, and quick inspection tells me that I need to take away 1. I can put a minus 1 there or just a minus. Now to bring it together, I've got 2x lots of x plus 4, minus 1 lot of x plus 4, so that gives me 2x minus 1 lots of x plus 4. And then I can double check my answer. The first is 2x squared, the outsides is 8x, the insides is minus an x, that gives me the 7x, and negative 1 times 4 gives me the last term, so I've got it. All right, the next one. Well, I can actually bring a common term out the front before I even start here. So I can actually bring a 2 out the front if I want to, and that gives me 4m minus 4 plus nm minus n. Now, what's going on inside the brackets? Well, here I can treat this as two pairs, similar to how I treated these 4 terms as two pairs here. So just factorising the first pair, I can have 4 out the front of m minus 1, but then I need an m minus 1 over here as well if I'm going to bring them together, and I can see that I need to put plus n in there so that I've got plus nm, and plus n times negative 1 is minus n. So I've still got my 2 out the front, but I've got 4 plus n lots of m minus 1. And I can tell that I've fully factorised it there because 4 and n share no common factors, m and 1 share no common factors, and I've got my 2 out the front there. All right, the next one, there's a right and a wrong way to do this. The right way is to say, hey, 3 and 27, they've both got 3 in common. Let's bring that out the front first before we even start with the rest of it. And then have a look if we can do any better. These don't share a common factor, but they are the difference of 2 squares. So I can see that they expand into x plus 3, x minus 3. Now, if I hadn't spotted that I could bring a 3 out the front at the beginning of that last question, I would have ended up in a world of hurt and have an answer that not only is messy, but is not fully factorized. So I'm going to do it the wrong way now, just to show you what that looks like, so that if you end up in a world of hurt like this, you know how to recognize it, backpedal, and actually go back to the beginning and do it the way we've done it here. So if I just treated this as the difference of 2 squares, which I know gives me 2 sets of brackets with a plus here and a minus here, and then if I take the square root of 3x squared, that's the square root of 3 times x, square root of 3 times x. Notice that the root sign is only over the 3, not the x there. And then if I use this as square root of 27, I could either write square root of 27 here and here, or you could write it in its simplified form, which is 3 root 3. Either way, you'd be tempted to stop there. Now, this looks very different from that. Firstly, it's full of surds, so it's a little bit nasty, but also it's not fully factorized. And the reason I can tell is if I look at these 2 terms here, they still share a common factor. They share root 3. So I can actually factorize these 2 better by bringing root 3 out the front, and that leaves me with just x plus 3 inside. But then I need to multiply that by these, the term here in brackets, which also I can bring a root 3 out the front of, and that leaves me with x minus 3 in brackets. Now you can see, I think, that the root 3 times the other root 3 will just give me 3, and if I multiply these together, I'm still going to get here. Now, okay, it's a clunky way to do it. You could still end up with the right answer using this method, but I think there's way more potential to make a mistake. Firstly, you've got to take the square root of 2 terms here, and you might make a mistake doing that. And then fiddling around with surds, I think you're just making it a lot harder for yourself. So that first step is really important. Always see if you can bring a common factor out the front first. Let's get rid of that not so nice version of the answer. Now, moving on to the next one. Looks like a non-monic quadratic trinomial, doesn't it? Similar to this one, but it's not. And how can I tell? 2, 10, and 12. I can bring a common factor out the front. So as soon as I do that, it makes my job a lot easier, because what I've got left inside the brackets is a monic quadratic trinomial. And we've seen that they're a lot easier to factorize, much quicker, much easier. So I can see here that I need 2 sets of brackets. I need x at the start of each one, and then I need 2 numbers that multiply to make 6 and add to make 5. So I need plus 2 and plus 3. And that was a lot easier than trying to tackle it with this method here. Potentially I still end up with the same answer. The problem is I might actually end up with an answer that looks like this. 2x plus 4 bracket x plus 3. If I'd used that method there, that's probably what I'd end up with. And the problem with that is, of course, is that the 2x plus 4, that's not fully factorized. So this answer is not as good as it can get. So look for that factor to bring out the front at the beginning. It saves you a lot of heartache and makes your answers better. All right, here we've got another one with 4 terms in it. So we're sort of stuck really with needing to use the 2 pairs method. So if I just look at the first pair here and see how we go. Now, sometimes when you've got 2 pairs, you can just use the first pair and the second pair and it'll all work out fine. If it doesn't work out, you might need to rearrange the terms and group together different numbers as pairs. Let's just see how we go here. If we bring a squared out the front, we're left with a minus 1. And then to bring it together in the last step, we really need a minus 1 in our second set of brackets as well. And that means we'd need a negative here. -1 or just a negative sign is enough. And I can see that negative a and negative times negative is a positive. That works out. So on the next line now, I've got a squared minus 1, lots of a minus 1. All right, it's tempting to stop there, but I'm not fully factorized. Why not? Do a squared and 1 share a common factor? No. Do a and 1 share a common factor? No. But now I can see the difference of two squares. A squared minus 1 actually is a plus 1 times a minus 1. That's that section here. And now I'm multiplying that by another a minus 1. So I could stop there, but is it as good as it can get? No, because now I can see that this factor and this factor are the same. So it would be a lot tidier to write this as a plus 1 multiplied by a minus 1 all squared. And this might look sort of similar to that, but it's actually quite different. There's no way I can factorize the stuff that's in the brackets like I could back here. So this version of our answer is actually far better. It is fully factorized now. All right, last one. Can we bring a common factor out the front? No. So here, perhaps we're stuck doing what we tried to do earlier, where we treated this just as the difference of two squares without bringing the common factor out the front. Now, the reason you might be stuck on this one is the 7. It's not jumping out as a perfect square. But we can still factorize something like this by saying, let's take the square root of the first term, 2x, and the square root of the second term, root 7, and then we've got a plus here and we've got a minus here. Now, it's a bit of a clunky factorization because it's involving surds and it's not sticking with integers. But if this was equal to 0, then it would be a helpful way of us actually solving the equation. If we needed to simplify a fraction and something had 2x plus root 7 on the bottom, we'd be able to potentially cancel something out. So a bit clunky, but possible. One final point. A very simple factorization nearly always will have two ways that you can do it. Now I'm talking about when you're just bringing a common factor out the front of a set of brackets. So if I have something simple like 3x minus 15y and I want to factorize that, the normal thing to do would be to say, hey, I can see that they've both got 3 in common, and so I need 3 out the front of x minus 5y. But what if we brought negative 3 out the front? That might be something you would do less often, but be prepared to refactorize round the other way if you need to. And remember the reasons that we might need to factorize. We might need to simplify some kind of fraction, and perhaps you want to bear in mind that you've got that flexibility up your sleeve as an extra tool. So if I brought negative 3 out the front here, well then I'd have negative x plus 5y. And that could also be written as negative 3, 5y minus x. So you've got that flexibility there. If you're looking for an expression that is the same as this and you're wanting to force it into a certain form, be prepared to do so. So down here where I'm simplifying this fraction, on the top I can see that I've got the difference of two squares. And on the bottom, I'm tempted just to do a basic factorization here by pulling 6 out the front, and that gives me 2 minus x. Now, the problem here is that I'm looking to do some cancelling now and actually divide the top and the bottom of this fraction by a common factor. But there isn't a common factor. These look similar to this, but not exactly the same. So I might want to refactorize here and say, look, actually, instead of 2 minus x, I'd rather have x minus 2 because I can see that I've got one of those on the top. So if I want to have x minus 2 and effectively have both of these terms in brackets with the opposite sign, I can do that by bringing negative 6 out the front. And that means that when I refactorize, I would have had negative 2 plus x, or x minus 2, which I could have written either way, whether you've written it that way or you've gone again. Now I can actually divide the whole top and bottom by x minus 2. Now, there's a few ways I can write my answer. I've got x plus 2 all over negative 6. Looks a little bit clunky to have the negative on the bottom. It's not wrong, but let's just bear in mind what we do with negative fractions. If I've got a fraction like negative a half, I could have the negative just hovering out the front. I can have the negative actually attached with the 1, or I can have the negative sitting with the 2. Those all mean the exact same thing. So effectively here I could say that this is negative x plus 2 all over 6. And in fact I could then expand brackets if I wanted to and say I've got negative x minus 2 all over 6. Now this is not wrong. this is not wrong, this is not wrong. They're all different versions of the same thing. But it's good to just know that when you have one of these answers and you want a different one, perhaps it's a multiple choice question and you've got an answer, but it doesn't look exactly like any of the options. You need to be prepared to play around with these sorts of things and find all of the disguises that are actually the same thing.